2 years in a row, 2022 and 2023. Yeah. But I will do the rest.
What about fractional distillation?
That's that is Rolls law. So they done fractional distillation.
Sorry, you freeze up. You have to go repeat what you just said.
All right. Yeah, and anytime you freeze, you'll let me know. Give me a second. All right. Now I'm just going to send you the answer booklet. So as I was saying, for module 3, when you're studying the topic, just ensure, because it's a lot of topics, but ensure you know so don't try to, Jaja. Oh boy. All right. Right. So I was saying for module 3, just study the equation, any relevant equation, any raw material, uses, and impact on the environment. Those are what the questions you usually surround. All right. So you can just look at the questions and the answer booklet. So if you need it, I sent my email in the chat. All right. All right. So let's get started with module 2.
People are asking for the PDF from Sunday also, okay?
Give us. I'm going. Oh, but they do on Sunday. All right. Yeah. I forgot about that one there now. All right. Yeah. All right. So immediately after the meet, just remind me to send it.
Okay.
Yeah. All right. So let's quickly get through this because I want to can finish by. Well, we're already being time. All right. I'm going to start off with calculations and end with these graphs. All right. So this topic. All right. So I'm strictly doing calculations. Now, with a topic like gravimetry, you must know like the uses, a limitation. So those questions, they will be in the answer booklet. All right. But I'm just doing the technical aspects. So you can just look at if they ask you for uses, you will see the answers. All right. Yes. So there are two types of gravimetry. This one is volatilization, where they ask you to calculate the number of moles of water. All right. This one, it's a standard type of calculation. So in this one, hold on, let me get the pen. A sample of washing soda was heated in a crucible to constant mass. The following observations were made. So with this type of question, they generally give you the mass of the empty crucible, then the mass of the crucible with the hydrated salt. So hydrated salt means it contains certain amount of water of crystallization in it. So if on a particular question, if you see they use the term hydrated salt, so they could have said hydrated washing soda. All right. That means it is before you heat it. So hydrated, it hasn't been heated yet. Anhydrous means after the water is removed. All right. So mass up the crucible and washing soda, and they give it the mass. Then mass of crucible and washing soda after eating, and they give you the mass. I'm going to label these. All right, A, B, C. So what you're going to do this calculation, right? You're going to need hydrated, the hydrated mass and the anhydrous mass. So to do that, you are going to subtract. So I'm just going to write it. So we're going to work out B minus A, and that will give you hydrated sodium sulfate. All right. So that would be 40.69, take away 34.25. If anybody have a calculator and can quickly assist. And then if you want the anhydrous,
6.44.
please repeat.
6.44.
All right, thank you. And then if you want the anhydrous mass of sodium sulfate, it will be the mass after heating minus the empty crucible. So that would be 37.07 take away 34.25.
2.84.
Thank you. So after you get the hydrated mass and the anhydrous mass, you are going to calculate the mass of water lost. All right. So to do that, it would be the hydrated mass minus the anhydrous mass. All right. So for this one, it would have been C minus A. So let me just put that C minus A. And then for this one, it would have been
Three point six gram for the water.
my internet. It's the internet. All right. Just tell me if you're hearing me clearly. No,
Yes,
this
sir.
internet. All right. All right. So 6.44 take away 2.84, and that gave me 3.6. All right. So after you get water, the mass of water that was lost, it's going to be like kind of like calculating empirical formula. So you're going to work out the moles of water and the moles of the anhydrous sodium sulfate. Give me a second.
So we
All
get
right.
0.6 from.
Hmm?
Oh, we get 3.6
Oh,
and a
right.
2.84
So we
from.
have to. No, man, we have to calculate the mass of water lost, which is the hydrated salt minus the anhydrous one. So 6.44 take away 2.84. How much I get?
3.6, but sorry for the sodium sulfate, you have 3.6 for the when you calculate the moles. It's supposed to be 2.84.
Right. Thank you. 2.84. And the molar mass for sodium sulfate, that would be, let me see, 20, 46,
142.
142. All right. Thank you. And what I get for the answer?
1 mole for H2 Na2SO4 and 10 mole for H2O.
No, man. As in, not the final answer here.
What am I get for? Oh, 0.02.
All right. So once you get the answers, you're going to divide by the smallest number. And so this will be 1 and this will be 10. Now this your answer here should always be 1. So if it's not, just check back your working out. Also, the moles of this salt should always be smaller than the moles of H2O. Right? Now, they don't have to give you the mass of the crucible and all of this, right? They could have told you that the mass of the hydrated salt is 6.44 and after heating it was 2.84. Calculate the value of x. So they don't need to give you all of this info. They could have simply just give you the mass of the hydrated salt and the anhydrous salt. Good. And you would just get straight to doing the calculation. All right. So this is one type of gravimetry, and that is how you would do it. The next type, let me see what is here. Not that, not that. Nope. Where is it? It seems I forgot to add it. Hope it's this one. Right. So the next type of gravimetry is precipitation gravimetry. Right? So this one involves, it's just like making us insoluble salt. So you would mix two solutions, you filter, you wash the precipitate, you dry it, and you weigh it. So in terms of precipitation gravimetry, it's mixing solutions, filtering, washing, drying, and weighing. Then we do our calculation. Right? And you should know the apparatus used. Right? Now, in terms of calculation, let us look at the question. It says a sample of impure potassium chloride of mass 0.450 was dissolved in water and treated with excess silver nitrate. A precipitate of silver chloride of mass 0.8402 was obtained. So when you're doing your good this type of calculations, they don't have to list the steps for you. They could just give you like 4 or 5 marks and ask you this question only. So they could just tell you to do this and give you 5 marks. All right. So the general steps: one, you calculate the mole of precipitate. All right. Then you write precipitation, precipitation, reaction. Three, you write the mole ratio and calculate mole of analyte. So whichever ion or compound you are interested in, you are going to calculate the mole of it. And then 4, if they ask you for concentration, you are going to calculate concentration. Or if they ask you for percentage, you calculate the mass, then percentage. So the general steps, then you are going to write the precipitation, reaction, mole ratio, calculate the mole of the analyte, and you're either going to calculate the concentration or the percentage. All right, so with that said, give me 1 second, let me just answer somebody. Right. So with these steps in mind, all right, I think the internet again chipped out. So let's go again. All right, so let's just continue. All right, so when we add potassium chloride, right, to silver nitrate, you are going to get silver chloride and potassium nitrate. So the silver chloride, it is insoluble. So this is the precipitate. So when they say calculate the number of moles of silver chloride, you are calculating the number of moles of precipitate. So as I said, you always start by calculating your moles of precipitate. So in this case, a precipitate of silver chloride of mass 0.8402. So mole would be equal to 0.8402 divided by 143.5, and you would get 0.0059. Then it says deduce the number
Sir,
of moles. Yes?
for the mole for silver chloride, what is the mole equal mass divided by RM, and the mass then give you for the precipitate divided by the RM of AgCl.
Mhm. Silver is silver is 107.
Mm-hmm.
Chlorine is
36.
35.5.
Mm-hmm. So it would have been 144 for AgCl.
No, 143.5.
Oh,
Remember, chlorine is 35.5.
mm-hmm.
Yeah. All right. So then now it says deduce the number of moles of KCl. So you would have your equation as I put it up here. So KCl plus AgNO3 to give AgCl plus KNO3. Right? Is 1 to 1. The mole of KCl is equal to 0.0059. Then it says calculate the percentage of KCl. If you want the percentage, it is equal to the mass of the compound divided by the mass of the sample times 100. So to get the mass now, we're going to multiply. So mass of KCl is equal to 0.0059, and that is 39 plus 35.5, 74.5. 0.44 grams. So the mass of this sample was 0.45. Just put it down here. So percentage is equal to 0.44, which is the mass of the compound, divided by 0.45, which is the mass of the sample, times 100. That is 98%. Now, generally with this type of question, you don't normally calculate a compound. It's normally an ion. So like the percentage of chlorine or the percentage of potassium. So normally the equation, it would have been an ionic equation. So like if we wanted to know the percentage of chlorine in the KCl, you would have just put silver ion plus chloride ion to give silver chloride. All right, so generally this type of question, we are normally interested in a specific ion. But in this particular year, they ask about a compound, KCl. But generally, it would be a particular ion. But the calculation is the same, right? It's just that if it's the ion, all you need to do is write the ionic equation. So silver ion plus chloride ion would give silver chloride.
So I can scroll some again to the can screenshot the bottom part.
All right. So that's gravimetry. Let's do, all right, not ready for UV as yet. That's UV, IR. All right, let's do the ans. All right, here's a titration. All right. What is this? All right, so it says a student standardize a solution of sulfuric acid using sodium hydrogen carbonate as the primary standard and found the concentration of the acid to be 5 moles per dm cube. Write a balanced equation for the reaction between sodium hydrogen carbonate and sulfuric acid. Remember to put your equations, to put your state symbols. Even if it was just 1 mark, still put your state symbols. You see, we'll end up with 0. In terms of balancing the equation, we would need a 2 in front of sodium. What else do we need? We need a 2 in front of water. Alright, so we have 2 hydrogen plus 2 hydrogen, that is 4. 2 twos, that is 4. 1 times 2, that's 2 carbon. So we need a 2 in front of carbon. 3 twos, 6 oxygen, 6 and 4 is 10. 2 twos, 4. 4 and 4 is 8. 8 and 2 is 10. So the equation is now balanced. So it says calculate the mass in grams of sodium hydrogen carbonate that the student would use to neutralize 23.5 cm cube of the acid were used from the burette. Alright, so if you want the mass, we know that mass would be equal to mole times molar mass. So what we need to get is the mole of sodium carbonate. But the only information that we have is the concentration of sulfuric acid and the volume of sulfuric acid. So the first thing we're going to do is to get the mole of H2SO4, and that would be equal to 0. So mole is, when you have volume and concentration, mole is equal to concentration times volume in dm cube. So it would be 5 mole per dm cube times 0. Remember, the volume is going to be in dm cube. So 0.02350 dm cube.
Zero point 1175 mole.
Thanks. 0.1175 mole. So now that we have the mole of sulfuric acid, we can use the mole ratio between sodium carbonate and sulfuric acid. So the mole ratio is 2 to 1. Right? So it's 2 NaH. Right, let me just put it down here. So second, so the mole ratio is 2 sodium hydrogen carbonate to 1 sulfuric acid. But you have to pay attention to which one you have the moles for. So because we have the moles for sulfuric acid and we want the moles for sodium hydrogen carbonate, you are going to multiply by 2, because you should have twice the amount of sodium carbonate as sulfuric acid. If you had the moles of sodium carbonate and wanted the mole of sulfuric acid, then you would have divided by 2, because the moles of sulfuric acid should be half the amount. So just look at the direction in which you are moving to know if you should divide or multiply. All right. So it would be 0.1175 times 2 and with 0.235. So now that we have the mole of the sodium hydrogen carbonate, we can go ahead and calculate the mass of it. That would be equal to 0.235 mole times, let me do that quickly, 48 plus 13 plus 23, 84.
19.74 grams.
Thanks. All right. So that is how you will get the mass of sodium carbonate. So generally, when you do a titration, you're always going to get volume and concentration of one of these substances. So you just work out the mole, write your balance equation, write the mole ratio, and calculate the mole of the substance that you need it for. So they could have asked you for concentration of sodium carbonate as well. But if they wanted the concentration, they would have to give you a volume. But because they only wanted the mass, then all you needed to do was multiply it by the molar mass. But if you wanted concentration, they would give you a volume and you would divide by it.
Sir, zoom up. I'm gonna take a
All
screenshot
right, so
again.
this is oh, all right. Put the equation in it. Let me just
Alright.
you have to just bear with this internet. Are you hearing me now again?
Yes, sir.
Alright. I'm plugging in the laptop. I'm in the country, so the internet is not so good. Oh, let me share back the screen.
Sir, you have to go start from the table part.
Alright, yeah. Give me a second.
Mhm.
Alright. Yeah, so it says determine the mean volume from the titer values to be used in the calculation. So if you were doing the titration. Where's the table? Right. So which set of values, if you were going to do the calculation, which of these out of these six, which would you use?
25.25 and 25.30.
All right. So what about the 3.5?
Oh yeah. No. Well, no, no, no,
Why not?
no, no,
As
no, no.
in, no, I'm just explaining. So the 3.5, into if you check it, the difference between the 3.0 from 3.5, it is the same from 0.25.
So
As
use
in,
3 and divide it by 3 then.
yeah, so you would use these three, four, 5, and 6. So it would be 25.25, 3.5, and 3.0. Because if you notice this, these three now, they are way off. All right. So these three are the three closest ones. All right. So let's do it now. On this one. Sorry, on there. It would be 25.25 plus. Oh, it just asks us to determine it. Well, it's just 25.35 plus 25.30 divided by 3. All right, let me do that quickly. 25.3. All right. When you get the booklet, you'll see this. All right. In terms of calculating, oh, it says using the following equation, justify the choice of the titer values selected in D2. So this is the formula for calculating standard deviation. So we just work out the average, which is 25.35. So when it says x minus x bar, x is each of these individual numbers, and you're going to subtract the mean, which is the average, from each of these, and then you square it. So you're going to say 25.25 take away 25.30 squared. Work out that for me, Shaniqua. And then you're going to say 25.35 take away 25.30 squared. And the final one, it would have been 25.30 take away 25.30 squared. So we know that this one is
Sir,
0. Yeah.
the 25.30, that
Mm-hmm.
is just that's another mean value. The mean value, you know, when you add up all of the items and divide it by the total number of items.
Now, so you add up these, right? So
But
the
remember
total
the
is
three closest values are the three closest something you use for this, you
mhm.
know.
Right. That's why you divide by 3, because of
Much
three
items
different.
in the table.
Shaniqua, yeah, use
Oh, I get
you know
it, I get it, I
yeah,
get it. No worries. Yeah.
right. And 25.25 take away
That would
25
give 0.0025.
0.0025.
Yeah.
All right. Let me get my other calculator. Sorry. All right.
Zero
So
point
20.
zero zero two five for the second one.
Sorry, repeat it. Oh, yeah, it would be the same. Yeah, 0.0025. All right, so this symbol here, it means the sum of. So you're going to add up all the answers. So that would now be 0.0025 plus 0.0025.
0.005.
0.005, and then n minus 1. N is the number of values that you are using. So even though 6 is in the table, we were using 3 of them. So n minus 1 is equal to 3, take away 1, which is 2. So now to finish the calculation, we are finding the square root of 0.005 divided by 2. So 0.00.
0.05 are the answer.
Yeah, thanks. All right. 0.05. All right. So when you calculate the standard deviation, right, it is telling you, it is giving you an indication of how close each value is. So if you get a very small standard deviation, it means the values are precise, very close to each other. And as you know, when you're doing a titration, you want to use the closest values. So your standard deviation, it should be very close to 0. All right. So the fact that this is a very tiny number, it means that the values were precise. So the very small value for the, I'm just going to put SD. So the very small value for the standard deviation indicates that the values used were precise. All
We
right.
can say if it's close or not close to the mean value.
Hmm?
We can
No,
state whether.
no, you don't need to be in this instance, right?
Mm-hmm.
So if you look at the question, it says justify the choice of the values you use. So because it's a titration, you must use the closest values. So this is justifying our answer because it is telling you that the values you use were very precise, which is what you should be using, values that are close to each other. If you were commenting on accuracy now, it would be a different thing because you would be comparing it to, you would be comparing one measured value to what is accepted to a true value. But with precision, you're just comparing it to the values that were measured. So the 25.25, the 25.35, the 25.30. So the standard deviation is telling you that they are very precise, which means that you would be justified in using them. Understand?
Yes, sir.
All right. 1 second. All right. So that's for standard deviation. If it comes, that is how you do it. All right. So we did gravimetry, we did standard deviation. Let me go to the titration question. All right. Oh, this was an next gravimetry. So let us do it a little quicker. So in this one, it says when 0.612 gram of hydrate. So you notice this time now it says hydrated. So this is the one containing water. All right. So 0.612 gram of hydrated barium chloride is heated to constant mass. 0.522 gram of residue is formed. So when you heat it, so 0.612 gram is heated and you get 0.522 plus the water lost. Right? So mass of water lost is equal to 0.612 take away 0.522. All right. So, oh, let me check that.
0.09.
So 0.09.
Yeah.
All right. So now barium chloride. What is barium again? Let me check that quickly.
137, sir.
All right, thanks. Bum, 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 bum. So 137 plus 71.
Oh, 71 and a BACL. Oh, 2.
B is still 2. 208. All right, so BaCl2 and H2O. So 0.09 divided by 18 and then 0.522 divided by 208.
So that would have given 0.025 more. 0.09 divided by 18. That would have given 0.005.
So it would be BaCl2 dot 2H2O. Right? So the water of crystallization is 2. So that's an easy 4 marks. I can screenshot that if I want, and then I move on. All right, so titration. All right, here is one. Let me wait. Hold on. All right, so this was the 2023 paper. All right, so it says 25 cm cube of aqueous solution of R requires 24.8 cm cube of 0.02 moles per dm cube manganate 7 ions for complete reaction. The equation for the reaction is that. Give me a second. All right, ready again. Right, so calculate each of the following. So first, it says calculate the moles of per manganate ion used. So remember, I told you in every titration, you have to get concentration and volume for one of the substances. So mole is equal to concentration times volume in dm cube. So it would be 0.02 times 0.0248 dm cube.
0.000496.
Yeah. All right, so that's the amount of moles of the per manganate ion. And then, right, so that was that. All right, so the next question now, it says the number of moles of iron in 25 cm cube of AQSR. So if you just look back here, 25 cm cube of an aqueous solution of R required this number of moles of the permanganate ion for complete reaction. All right. And R contains Fe2 plus. So the mole ratio between the permanganate ion and Fe2 plus is 5 to 1. All right. So when it asks for the number of moles of Fe2 plus in 25 cm cube of AQSR, we're going to use mole ratio. So it is 5Fe2 plus to 1 MnO4 minus. And we have the moles of this, and we want iron. So we're going to multiply it by 5. So it would be equal to 4.96 times 10 to the minus 4 times 5.
Sir, I'm kind of lost, you know.
All right. So it tells you that you so it's a regular titration. It's a redox titration, right? But the same calculation. So if you have the moles of this and you want the moles of this, you're going to use the mole ratio, right? 5 to 1. Is it because it says the number of moles of Fe in 25 cm cube of R?
Yeah.
Oh, no, man. So if you look, don't make that throw you off, man. Remember, it's a titration, So you have 25. So look, just imagine you have a conical flask, right, with 25 cm cube of R, right? So whatever amount of Fe2 plus is in the 25 cm cube, that is what is reacting with MnO4 minus. So it's like saying if you prepare 25 cm cube of FeSO4 in the conical flask. So 25 cm cube of R, it contains some amount of Fe2 plus. So the Fe2 plus in the 25 cm cube, that is what is reacting with MnO4 minus. All right. So this amount of mole reacted with whatever amount of Fe2 plus that was in the 25 cm cube. All right. So it is just asking you for the number of moles of Fe2 plus in the 25 cm cube of iron sulfate. sulfate. All right, yeah. So you multiply it by 5 and you get
Yeah,
2.
freeze there.
Right, yeah. May realize it it go on. What take it off? Yeah, it a freeze. Want it to move so slow. It a freeze. Are you hearing me clearly again, or it's still
It good
breaking up?
now.
All right. So let me continue now. Right. So 2.48 times 10 to the minus 3. Then it says the number of moles of Fe2 plus in 1 dm cube. So remember 1 dm cube, right, let me put it down here. 1 dm cube is equal to 1000 cm cube. So we're either going to be working in cm cube or in dm cube. All right. So it wants to know the amount in 1 dm cube. So this amount, so 2.48 times 2.48 times 10 to the minus 3 mole is in 25 cm cube. So we need to find out now how much would be in 1000 cm cube. Right? So you just cross multiply. So x is equal to 2.48 times 10 to the minus 3 times 1000 divided by 25. All right. So let me just do that quickly. So times by 1000 divided by 25.
0.0992.
Right.
Mm-hmm.
0.0992 mole. All right. And then now it says the mass of iron in 1 dm cube of R. So this is the number of moles. All right. If it had said the mass of iron in 25 cm cube of R, you would have multiplied this number of moles by the molar mass. But it says in 1 dm cube. And this amount of moles of iron would be in 1 dm cube. So remember, mass is equal to mole times molar mass. So it would be 0.0992 times 56.
5.56.
That would be right, 5.56 grams. And then it says the percentage of iron in the compound. So remember, if you want percentage, it is the mass divided by, so the mass of compound divided by the mass of sample times 100. All right, so just check. They did not give you the mass of the sample, right? But let's look what they did. If they give you an information, it means that you're supposed to use it. All right, so the the mass concentration of R is 40 gram per dm cube. So why did they give us the mass concentration?
And,
To find the mass.
if I have any problem, I'll just delete it and download the other one.
Right, so how we do that?
Or
So
is it just what he's
if you
It
streaming?
times it by the
hold on,
volume.
Because he is
give me
streaming.
a second. Somebody else mic is Somebody else mic is on. I'm trying to pick up who. All right. All right, let me mute. All right. Right. So remember, this 5.56 gram of Fe2 plus is in 1 dm cube, and the mass concentration of R is 40 gram per dm cube. So it means that 40.9 gram of R. Am I freezing? Because it's moving a bit slow. Are you hearing me clearly?
Yes, sir.
All right. So 40.9 gram of R is in 1 dm cube, and 5.56 gram of Fe2 plus is in 1 dm cube. So it would be 5.56. So the mass of the sample would be the mass of R. So 5.56 divided by 40.9 times 100. And that would
So
give
what them the all of
me,
that for?
just to make things a bit difficult. Yeah, so I have to just pick it up. So 5.56 divided by 40.9, 13.6%. Yeah.
Sir, zoom out so my
That
screenshot
means
appear.
you can take a right. Let me, yeah. Hold on. Yeah. Oh, let me save as well. So, all right. So that was a regular acid base. Well, this is redox, but acid base and thermometric titration. So with thermometric titration, acid base, and redox titration, the calculations are the same. All right. It's just the method which I use. And redox and acid base use the same method. It's just that redox, you do not use a titrate, you do not use an indicator. All right, hold on, not this. All right, I don't think they will do it, but I'm going to work it just so it don't come tomorrow. It's back titration. All right, so we're going to do one back titration so it don't come tomorrow. All right, so it says a student was asked. So remember in our back titration, so let me just put it here. Back titration. You have your reaction. You have your reaction. Hold on there. Sorry. Reaction and titration. So back titration, two things are occurring. We do a reaction and then we do a titration. So a student was asked to determine the purity of a contaminated sample of ammonium chloride. The starting of the question, it's always the reaction. And the ending of the question contains the information for the titration. So it says a sample of 5 gram was warmed with 100 cm cube of 1 moles per dm cube sodium hydroxide. Right, so this information is for the reaction. So whatever moles is used in the reaction, that will be the total. Because remember, we always use an excess amount in the reaction. So they're going to give you the concentration and the volume, and you work out the number of moles. if they don't give you concentration and volume, they tell you the number of moles, then that is the same thing. So if you get concentration and volume, you work out the moles. If they choose to give you the moles already, then that is less working out. All right. But they did not give you the number of moles. So the first thing I want you to do, calculate the total mole of NaOH. All right. So that would be 1 moles per dm cube times 0.1 dm cube. So that would be equal to 0.1 mole. And then you're going to write an equation for the reaction, which is ammonium chloride with sodium hydroxide. So when ammonium chloride reacts with is it freezing?
A little.
Seems to be right, because it moves slow. Right, let's give it that 3 seconds and see. Let me just tilt it a little. Alright, so let's try it again. So sodium chloride plus sodium still freezing. It seems like it's still freezing.
No, you're good.
Alright. Sodium hydroxide. So when you react, no, just like freeze. Alright, so when you react an ammonium salt with sodium hydroxide, you are going to get going to get a salt. You sure it not freeze? Because this move slow. Right, so you're going to get salt, ammonia, and water. So it's just like when you react carbonate with acid, and you get salt, carbon dioxide, and water. So with this one, you get salt, ammonia, and water. So you're going to do two things at the start. For the reaction, you calculate the total moles and write a balanced equation. Then you move over to the titration. All right. So it's sorry. So it says after all the ammonia had been driven off, the excess. When it use excess for the titration, it means unreacted. All right. So the unreacted. So because you use more than enough sodium hydroxide in the reaction, not all of it is going to react. So whatever is left over, the excess, the unreacted, same thing. Whatever is left over, that is what we use in the titration. So the unreacted sodium hydroxide required 25 cm cube of zero point 0.5 moles per dm cube sulfuric acid for neutralization. So just like with the reaction, you are going to calculate the number of moles. So you're going to calculate the mole of sulfuric acid, and that is equal to 0.5 times 0.02. What just happened? 0.5 times 0.025. and that is equal to 0.0125. Now, after you do that, you are going to write a balanced equation. So it is sodium hydroxide plus sulfuric acid to give Na2SO4 plus H2O. Remember to put your state symbols. Let me just do it. Aqueous, liquid, aqueous. And put it for everything. Don't put it for some and leave out some. All right, so the mole ratio now is 2 to 1. So what you're going to do is calculate the mole of the unreacted sodium hydroxide. Mole of unreacted sodium hydroxide is equal to 0.0125 times 2, and that is equal to 0.025. So since you have the mole of the unreacted sodium hydroxide, what you actually need is the mole of reacted. I'm just phrasing it like this. So the mole of reacted NaOH, and that is equal to the total. So remember the total from the reaction minus the unreacted from the titration. So it's the total minus the unreacted, and that would be 0.1 minus 0.025. All right, and that should give us 0.075 mole. All right, so once you get the number of moles of sodium hydroxide that actually reacted with the ammonium chloride, then you come back to this equation. All right, so the titration is to get the number of moles of sodium hydroxide, then you subtract it from the total that was used in the reaction. Once you do that, you come back here now because you need the mole of ammonium chloride. So mole ratio is equal to 1 to 1 for ammonium chloride and what, and sodium hydroxide. So mole of ammonium chloride is equal to 0.075, and so we can find the mass now. Is equal to 0.075. I think it's 53.5 if I remember correctly. 35.5 plus 15, no, plus 17. Yeah, 53.5. So 0.075 times 53.5, 4.01. 4.01. So the percentage would be 4.01 divided by 5, because remember the mass of this sample was 5 grams times 100. I think that should be 80%. So back titration is a bit long, but the process is standard. at the start and you write the equation. Then you move to the titration, calculate the mole of either the acid or the base, whichever is given, and you write the equation, write the mole ratio, and you calculate the mole of the unreacted, in this case, sodium hydroxide. Once you get the unreacted, you subtract it from the total to get the amount that actually reacted. And this is what you apply now to the equation. So you can get the mole of ammonium chloride. If they wanted concentration, instead of mass of the sample, they would give you a volume and you divide it by it and get concentration. But if they want the percentage, they give you a mass. And this is what happens. Alright, so you can go ahead and screenshot and we move to the next question. Alright, so let's move to a next one. Alright, so that's titration. Where is UV? Let's do UV quickly and IR. No, not going to do any more titration. Alright, here's a UV. Well, not necessarily UV, but it's a part of it. So you should remember this equation. Remember E is equal to, remember this equation, E equal H V. And what's the equation that relates C, F, and lambda? Well, it's here already. But what's the equation that relates these three? Anybody remember? All right, so hold on. Can you go over the part moles of sodium hydroxide reacted? All right, let me do this quickly. Where let me just answer someone quickly with the back titration. Where was it? Right. So at the start of the question, they gave you the concentration and volume of C that is used. And then in the titration, it's what is the amount. So you subtract the unreacted from the total and you get the amount that reacted. So, right. So just remember, if you don't remember how to arrange this, just remember these two are inverse to each other. So frequency should be 1 over lambda. Lambda is 1 over the frequency. And you would just replace the 1 with, sorry, hold on. You would just replace the 1 with C. Alright. Yeah. So the two of them have an inverse relationship. So the bigger the frequency, remember this formula. And then C would be the frequency times the wavelength. Sometimes we switch out F with V. All right, so F and V are used interchangeably. All right. So for this question, it says the amount of energy, see it better. the amount of energy absorbed by one molecule of a compound. Oh, calculate each of the following of a
Sorry, I freeze.
compound where V is equal to this and H is Planck's. May I break up?
Yeah.
Alright. Let's see what I'm going. I don't know. It sounds like may I break up same way?
No.
Alright. Where's I'm put the pen? Let me see it. Alright, so H is Planck's constant, V is the. Alright, we have the answer for V here. Alright. So so E would be equal to 1.5 internet up 6.63 times. And this I move really slow. Yeah. All right, let me do this quickly. Calculate it. Bam, bam, bam. Where's my calculator? Right, so 6.63 expo negative 34 times 1.5 ex. Sure. 6.63. Right, we're at 9.95 times 10 to the minus 19. Yes, it will be posted. Just click on the live. Just click on the live tab and you will see it. All right, let me show you quickly. Give me a second. Let me just. Someone is asking if it will be posted. Just give me a. Where is it? Just a second. So just when you come on the channel, just click this button, all right, and it will be there. So just click this button and you will see it. All right, so the answer was 9.95 times 10 to the minus 19. When they ask you now, so it says the energy absorbed by 1 mole. So when they ask you for 1 mole, just multiply this answer that you get by Avogadro's number. So 9.95 times 10 to the minus 19 times 6.02. And that would be 5.99 times 10 to the 5. All right, you can screenshot this if I want. Let me save again. All right. All right. So since we're on UV, all right, yeah, let me look for the UV one now.
Sir, the unit for that are joules, right?
All right, let me start here.
The unit for that are
What were
joules,
we
right?
calculating? Energy?
Energy. Mm-hmm.
If it was energy, yeah. Yeah. If I, yeah. Energy. All right. Right. All right. So for this, oh, you should know your electromagnetic spectrum. So you should know what frequencies correspond to like IR, UV, radio wave, X-rays. All right, yeah. All right, so it says U1 um, from B1, it was referring to this formula where C would be equal to the frequency times the wavelength. Or if you want to put C equal V times lambda. All right, relationship. So if you want frequency, hold on. If you want the frequency, it would be C over lambda. And if you want lambda, it would be equal to C divided by the frequency. But remember, you can use F or V. All right, so F is the same as V. All right, yeah, all right. Right, so we're in here now. If you want the frequency, the speed of light is 3 times 10 to the 8, and the way and you have the wavelength. So bam, bam, bam. Which one is it? We want frequency, so it's speed of light divided by the wavelength. So it would be 3 times 10 to the 8 divided by 1 times 10
3 times 10 to the 13.
to the 5. So we can do that. 3 times 10 to the
13.
internet break up again. All right, say that again.
3 times 10 to the 13.
Yes. Well, on there. Let me see something. Oh, a negative 5, not positive 5. Get it used? Yeah, a negative 5 get it used. All right. When I give you the answer booklet, you will see the answer for the wavelength. I mean,
3.8.
the EMR. 10 to the 8 divided 0.49 times 10, 3.6.
3.16. Yeah, 1616.
All right. All right. And then it says, when when a covalent compound absorbs UV radiation,
Yeah,
electrons are
yeah.
promoted. This phenomenon forms statement here is also the answer to a question they could ask. So it clear back up? I freeze.
Yeah, all right, no.
Still sound like it a freeze? Alright.
Mm-hmm, all right.
for it, which is that electrons
Sir, when I
in
see your screen,
bonding. All right, let me reshare. Are you seeing it now?
yes, sir.
All right. So right. So like it has. Yeah, hear me, cause it's you're breaking up. So tell me if you can hear me clearly.
You're in and out sometimes.
Yeah, hear me clearly. Hmm? Shanika? All
Sir,
right,
yeah,
I'm gonna
free.
assume you not hear me clearly. Right. So you should be able to tell the your internet a bit. No, no, go on. All right. Still a freeze, man. I don't know if it get any better. All right. Are you hearing me?
Yeah.
All right. Right. So they can ask you the basis for UVVs. Just remember bonding, molecular orbital, bonding, molecular orbital, and above that you have anti-bonding, molecular orbital. All right. The electrons are down here. All right. When they absorb UV light, they move up here. These are empty. All right. So the anti-bonding orbitals, they are empty. The bonding ones, they have the electrons. They are lower in energy. So the basis for UVVs, electrons in bonding molecular orbitals absorb UV light and move up into higher energy anti-bonding orbitals. All right. So just to keep it simple, electrons in bonding molecular orbital absorb UV light and move into anti-bonding molecular orbitals that are higher in energy. All right. Yes. So that's like a 2 or 3 marks questions. All right. To explain the basis. But if you don't remember anything, just remember electrons absorb it. You can at least get something. All right. If you notice, I mentioned the term bonding molecular orbital, right? So you have sigma, you have pi, and you have non-bonding. So these are your bonding. uh, So these three are your bonding molecular orbital. And these two now with the asterisks, those are your anti-bonding. Sorry, these are the anti-bonding molecular orbitals. Now electrons, each of these, right? Each of these bonding molecular orbitals, they can make two transitions. So all possible transition, you have a total of six because each of these can make two transitions to the anti-sigma and the anti-pi. So each of these, they make two transitions. They can go into the anti-sigma and the anti-pi.
Sir, what does the N stand for again?
Non-bonding.
Okay.
Yes, so N is non-bonding. All right. this with the asterisk, it is anti sigma, and the pi with the asterisk, that is anti pi. That is just pi, and that is just sigma. All right. So once they have the asterisk, those are the anti-bonding ones, and they are empty. That is why the electrons can go up there. So if they ask you for all the possible transitions, just draw two lines from each of these and put one here and one here. All right, so those are all the possible transitions for UVVs. All right, so when it comes to UVVs, at least remember the transition. You must remember the basis. Electrons move from bonding to antibonding when they absorb UV light. All right, so that's the
So
basis.
you never finish the chamber up there, so.
Um, yeah, this I answered. Because when me send you the booklet, me remember the specific EMR for these numbers, but it will be in the booklet because I think we did it Sunday as well, so it will be in that one. All right, yeah. All right, so you can take a screenshot of this if you want. Let me just zoom out. All right, so know your transitions. All right, the next question now, not that one. Where is it? Right, this. So it says list the transitions from C1. So this was C1. So out of all the possible transitions, it is asking us to list which will normally produce absorption in UVV's electromagnetic spectrum. And a next way they ask it, right? Which transitions are used in UVV spectroscopy.
Sir,
So
pi.
outside of asking you for all the possible, just a second, outside of asking you for all the possible transition, the next thing they're asking you for is the ones that can actually be used. You can go ahead, Shanika.
It would have been pi, right?
Pi to, so you can't just say pi, it has to be pi to something.
Pi to
So
anti-pi.
pi to anti-pi can work, and
Um,
then so it's just pi
none
and
to
then you
the n, so the
right
anti-n.
non-bonding to anti-pi and non-bonding to anti-sigma. So pi it just goes to anti-pi, but non-bonding goes to both of them. So these are the ones that are useful. All right. So those are the useful transitions. So you should know all six, and then you should remember the three that we use. All right. And those are the three. Now, let me just mention it here because I don't think it's in any of the papers I got here. You have a molecule, you have compounds that we call chromophores. All right. So I'm just going to put something short here. So compounds, you can just check for a proper definition, right? But for your understanding, right? Chromophores are compounds with a lot of double bonds and are, well, they usually have a lot of double bonds and lone pairs. And lone pairs. So for example, this compound here, like a benzene ring, let me just fix that up. Like double bond, double bond, double bond, and then like let's say of this, then double bond O with the lone pair. So a chromophore, it has the double bonds and lone pairs, and it is used to increase the absorption. All right. So if you're analyzing a sample and you want to increase the amount of Fe2 plus in a sample, in a water sample, and you want to add chromophore to it. So the chromophore would be something with a lot of double bonds and lone pairs. So the chromophore is to increase the. So for example, if I ask you, why am I analyzing? So let's say you have a sample with this, right? What is the purpose of adding this compound to the Fe2 plus?
To increase the amount of absorption.
Once you see I am adding a compound to Fe2 plus, and you see the double bonds, just know it is a chromophore used to increase the absorption, right? Okay, yeah. For UV we mentioned the basis of it. We looked at all the transitions and we looked at the useful ones. I tell you about chromophores. Outside of this, you must know to do the calculation. All right. Hold on, wrong thing. I can take a screenshot if you want this info because I'm going to clear it off.
So this is the topic with the calculation A equal ECL.
Right. Yeah.
Okay.
What year's paper is this one?
Also, before I do the calculation, right? Please repeat.
What year's
All
paper
right.
is this?
I guess it's something, let me see, 2019. Yeah, the years on this one. So 2019. All right, before I
Okay.
do the calculation, there's one more thing. Yeah, with UVVs. So let us say, right, we're analyzing. So one of the applications of UVVs, you can determine the concentration of ions in a sample. So for example, if you want to know the concentration of chloride ion, or let's say Fe2 plus, right? You're going to plot a calibration curve. All right. So the calibration curve is plotting absorbance, absorbance versus concentration. And what you would do, so they can ask you about this, right? You would make a series of standard solutions. All right. So you're going to make standard solutions. So if you want to know the amount of iron, if you want to know the concentration of iron in a sample, you're going to make standard solutions of Fe2 plus. All right. So for example, you could use iron sulfate and you make a series of standard solutions. All right. And you're going to take the absorbance reading. All right. No, the instrument we use is called a spectrophotometer. So you should know how to use it. All right. There's a question with it as well. I don't remember which year, but essentially, what you do, right? You're going to, all right. So to take the absorbance reading, you have to use a spectro. Sometimes this is spectrometer or spectrophotometer, right? Two key things that you should do, right? You have to blank. So this is how we say it, all right? You blank the spectra. So before you take the absorbance reading, you have to blank the spectra photometer, and it has to be set at a desired wavelength. All right. So in using the instrument, you have to set it at a desired wavelength, and you have to blank it. Just put back this term. They will know what it means, but I can't go into the explanation and the reason for it, right? Yeah, so make sure that the blanket you should not get any reading, right? And you blanket using distilled distilled water, right? So and the instrument we put inside of it, so a little cube thing, it's called a cuvette, all right? So when you're using the spectrum, the solution inside your cuvette, put the cuvette in the spectrophotometer absorbance readings. All right. So if you're analyzing a sample, for example, to determine the concentration of iron in water, you put the spectrophotometer and take the absorbance reading. All right. But before you do that for the standards, you would blank it using distilled water. All right. Yeah. So you must know the process of using the spectrophotometer. All right. So what will happen? You will take the absorbance reading for the standard solutions that you made. You will also take the absorbance reading for the sample. Then you plot a graph of absorbance versus concentration. You are going to get a straight line. Then now to get the concentration of the sample, it will have an absorbance reading, right? You just extrapolate it from the graph. All right. So the purpose of the calibration curve, the purpose of the calibration curve is to get the concentration of the sample. All right. That's the only purpose. We want to get the concentration of this sample. So we plot the absorbance versus concentration, and we extrapolate the absorbance reading to get the concentration of the sample. All right, so this, it will give the concentration of the sample. All right, yeah. So let's get to the calculations now. So if you want to take a screenshot, you can, but I'm going to clear the board now.
Sorry, you're gonna steal the Rahul?
Please repeat.
You're gonna
Yeah,
steal the
yeah,
Rahul?
yeah, yeah. You mean Rolls law?
Yeah, that.
Yeah, yeah, yeah. Me, I'll go to it after this. Alright. Why this not about? freeze the computer, freeze up. The page cannot freeze. I don't know where I'm going. Alright, but I have enough space to work it still. The absorbance reading of iron thiocyanate solution containing 0.005 iron per milliliter was reported at 0.49 at 500 nanometer. Use Beer-Lambert's law to calculate the specific absorptivity, including units of iron thiocyanate, assuming that a 1 centimeter cuvette was used. When they assume that a 1 centimeter cuvette was used, something is this. Um, something is off. It's not responding. Now, person asking if module 3 is going to be covered. I'm going to send an answer booklet for module 3. What you need to focus on, right, for module 3, know any equation that is there, ensure you know your equations, the process, uses, and environmental impact. So even if you're doing the contact process, know the uses of sulfur, impact on the environment, the equations, all right? Yeah. This, hold on, I need to close this. It's not responding. Yeah, I don't know what just happened. All right, so let me just find back the document quickly. All right, so let's do the road slug question. All right, so just to check, are you hearing me clearly? I'm not sure if you're hearing me. Are
Yes,
you hearing
sir.
me? Just check. All right. All right. So yeah, let's just get because it's late now and you need to go and study other things. All right. So I'm just going to point this out. All right. When you get a graph like this, it's an azeotropic mixture. All right. So if you see a graph like this, it's an azeotrope. So let me just make a note of that. All right, so if you look at the first graph, right, this is not an azeotrope. This is a normal diagram. This one, it's an azeotrope. As once you see it meets anywhere in between these two lines, it is considered an azeotrope. All right, so it's an azeotropic mixture. All right, when you have an azeotropic mixture, and so give me a second. All right, so see, so this is an azeotrope. All right, I'm going to just explain it, and you can look at the written answer afterwards. All right, in the booklet. So I'm just going to explain it because time is going. So this here is an azeotrope. So remember these graphs, right? This one and this one, it is dealing with fractional distillation. As you know, with fractional distillation, you are trying to separate two liquids with similar or close boiling points, right? So what happens when you look at this here, you're not going to get 100%. So if you have an azeotrope, you cannot, so just know that you cannot get 100% composition. All right. The reason why you see at this point here, so if you look on the x-axis, right, out this line is 100% A. So when you get to this point, you would have separated A from B completely. So you have 100% A. On this side, so if you start out over here, when you get to this point, you will have 100% B. So if you are doing fractional distillation, you are trying to get either 100% A or 100% B from a mixture of the two. Now, first of all, right, look at the boiling point of B and look at the boiling point of A. The boiling point of B is higher than A. That means that A is the more volatile component, right? So when you heat it, when you heat a mixture of A and B, the vapor will have in more A than B. Now, what is the importance of this graph?
Sorry,
Remember,
you
the purpose of showing out over here. Sorry, I'm breaking up.
Yes, sir. You
Shanika,
forgot to repeat.
are you
You
hearing
forgot.
me?
Yes, sir. You forgot to repeat.
All
Mm-hmm.
right. Yeah, man. But as long as you're hearing me now, right? So if you see a graph like this, as I said, it is an azeotrope. What it means, you will have when you get to this point here, right? The mixture at this point M, so I'm pointing it out. At M, it behaves as a pure liquid. To understand this, right? If you have water, can you separate water from water?
No, sir.
Not a mixture, as in, right? So if you have salt water, you can separate the salt from the water. So what I'm trying to tell you now, right? You see at this point where the two lines touch, it is behaving as a pure liquid. What that means, you cannot separate it. So that is the reason why you cannot get 100% composition. because right here where the two lines touch, if you look at the composition, right? If you should, if this is what, if both ends are 100%, in the middle here is about 50%, right? That means at 50% you cannot get any more, right? So when it says use the graph, explain clearly the result of distilling a mixture of X as indicated. So this is what will happen, right? The bottom line, it is called the liquid composition. All right. The top line is the vapor composition. Vapor composition. So you have the liquid. When you boil the liquid, you will get the vapor. All right. So what we are going to draw a line from the liquid to the vapor. All right. What I'm going to do for you, I
Sir.
have a recording on this, but it's a private class. But I will just open it. Yes.
So B, so
Are you hearing
B,
me,
A, I gonna be more readily,
Trenico?
yeah, gonna be more readily vaporized than B because it has a lower boiling
Yeah.
point. Okay.
Right. So you, if you are asked to explain, right, what you are going to do. So starting at X, you are going to draw a horizontal line touching the vapor component, and then you draw it come back down here, right? So remember, in fractional distillation, what are you doing? You have a liquid mixture, you boil it, right? When it vaporizes, you condense the vapor, and then you're going to re-boil it again. So starting with this component, right? This is the liquid component or the liquid composition. When you boil it, you're going to get a vapor composition. So you have a liquid, you boil it, and it will become a vapor. You are going to collect the vapor and condense it. All right. And you have it in a new container. So the vapor, it will have in more of A than B because A has a lower boiling point, so it will vaporize quicker. Now, what you are going to do, right? You are going to, you are going to get to this line now, all right? Hold on, and draw it here, and then you draw it come down. Hold on. So what is happening, right? Sorry. On this side, it would be 0A, right? So if you have 100% B, you would have 0A. And out here is 100% A. So when you start with a mixture of, let us say, 20% A, notice after you boil it and condense it, it is getting richer in A, right? Because you're going across to the left hand side, right? Understand? So if you start out with 20A, this point here, let's say it is about 30, and then this point it is about 50, right? So each time you boil the mixture, condense it, re-boil it, you are getting a higher percentage of A. Understand, Shanika?
So you
Or
say
you
because
still
you
there?
start off with A, that's why you get a more higher percentage of A than B.
Sorry, ask it again.
Because you start off with A, you get a higher percentage of A compared to B.
No, you have a mixture of A and B, right? So what you have
Mm-hmm.
to do, look at the x-axis. Hold on. Look at the x-axis. So if you're starting here, right? Hold on. If you're starting at this point, remember it is close, this point here, it is closer to this axis, right? And this axis, it says what? 100% B.
Yeah.
So this, right? So the axis with 100% B, it would have 0% of A. So if you are starting at X, it would have the mixture. So X is a mixture now. So you see this line here, it is 100% A. So anything in between is a mixture of, which is X. It is much closer to B. So this mixture, so X is representing a mixture of A and B, but it would have more of B in it, seeing that it is closer to 100% B. Before I go any further, you understand what I just said?
Yeah.
All right.
Yes.
So your start, so this X here is representing a mixture with more B than A in terms of percentage, right? Now, if A has a lower boiling point, when you start to boil the mixture, will A come up first or B?
It will come first.
A.
Right. So remember, B it has a higher boiling point, So you look at the curve. So the boiling point for B is up here, and the boiling point for A is down here. So B it has a higher boiling point than A. So when you start to boil the mixture, A would escape as a vapor quicker than B. So that is why this line here, right? When you boil this mixture, right? The vapor, it will have a higher composition of A than B. All right. So, well, not at this point, but what is happening is that the vapor, it will have in more A than you initially started out with. So what you're doing is reading the line. So I'm saying at this point X, right? For example, X is 70% B and 30% A. So we're going across. When you get to, I'm going to call it X1. X1 will probably, let's say, 65 or 60% B and 40% A. So you can see that after the first time you boil the mixture of A and B, the amount of A that you are getting, it increase, right? Do you
Yeah.
understand? I need to know.
Yeah, cause it more
All
vaporized
right.
compared to B.
So you right. So X1 now, right? That's a liquid. So the composition X1, let us say it is 60% B and 40% A. Composition X was, for example, 70% B and 30% A. So after you boil the mixture, you're getting a higher percentage of A and a lower percentage of B. Now, if you boil X1, notice now, let me put a next, what color ink? Let's call this one now, right? X2. Let's say X2 is 50% B and 50% A. Pay attention to what is happening. You started out with 30% A. The first time you boil it and condense it, it reached 40% A. The next time you boil it and condense it, you have 50% A. Remember, fractional distillation, you are trying to get 100%. So what this is showing, right? And let me go to this graph here. What this is showing you, when you start out here with this composition, This is the liquid, right? And you boil it and you collect it. You get a richer, you get a richer mixture containing A. Right? Let me do it a little better than that. Right? So you have X, you touch the liquid line, you draw it across to the vapor line. Wherever you touch, you draw it come down. What this is telling you have a higher percentage of A than you initially started out with. When you draw the line come down, right? Wherever it touches the liquid line, so it touches it here, you draw a line across. All right? Wherever it touches the vapor, you draw it come down. So if you look at X2, comparing X2 to X, which one has in a higher percentage of A? X2 or X?
X2.
Exactly. So this, you see this graph, it is showing you how fractional distillation works. Every time you boil the mixture and condense it, you are getting a higher percentage of the more volatile substance. And that is what the graph is showing. So just remember, you look at your x-axis, all right? Out here, you are getting 100% A. Here, you are starting with a mixture of A and B, right? So you have a mixture of A and B, but what you want is 100% A. Here it says boiling point, right? So this is a boiling point composition curve. The boiling point of B is higher than A. That means A is the more volatile substance. So you are going in the direction of the more volatile substance. So each time you boil the mixture and condense it, you are getting more and more A. So you see after X2, if I should draw a next line, the next time I boil X2, I am going to get 100% A. So from a mixture of A and B, I was able to get 100% A just by boiling the mixture, collecting the vapor, reboiling. So with fractional distillation, right? You boil the mixture, right? Condense the vapor, condense the vapor, reboil. Let's say I'm going to put reboil the condense because I want you to understand what is happening. So you reboil the condense vapor, then you condense the new vapor. So it's just a continuous process of boiling and reboiling. But what is happening each time, the vapor, the new vapor, it is richer in the more volatile substance. So when you get the graph, right, you look at it. Which one has the higher boiling point? Which one has the lower boiling point? If they did not put any line on this, right, you would need to know that you start from this direction and go across. Reason, B as the higher boiling point, A as the higher, sorry, A as the lower boiling point. So you are trying to, if A as the lower boiling point, it is more volatile. Lower boiling point means more volatile. What does that mean? I'm just going to put equal. More of it is in the vapor. All right. So you're always going to have more of A in the vapor phase compared to B, because A has the lower boiling point, so it is more volatile, so easier into the it will escape easier as a vapor. All right. Yes, so that is what this is showing. So when it says use the boiling point composition curve in figure 6 to explain the principles of fractional distillation, starting with a liquid of composition X. So let me just say this last time. The purpose of fractional distillation is to, so fractional distillation is a separating technique. You want to get 100% of a particular substance, of a particular liquid, right? Look at the composition, look at your x-axis. This is B with the higher boiling point, this is A. What you're going to say, right? If I'm starting with liquid composition X, right? When you boil it, it will have a vapor composition A1, right? When you condense the vapor, right? Clearly, the liquid composition X1, it is richer in A, all right? Now, if I boil the new liquid composition X1, I will get a new vapor composition A2, right? When you condense the vapor, you realize that it is even richer in A than it was before. So each time you boil the mixture and you condense the vapor and reboil, you are getting a mixture more pure in the less in you are getting a mixture that is richer in the more volatile substance, which is A, the one with the lower boiling point. So if you continue doing that, you will get 100% A. All right. So just by boiling and reboiling, you will get 100% of A. All right. Now, if you compare that to this graph, remember I told you that this is an azeotropic mixture, you will not get 100%. When you get to this point, it stops. It doesn't matter how much you boil and reboil, it won't change from, let us say at this point, it is 50-50. It is not going to change because it is behaving as like it is a pure liquid. But we use the term constant boiling mixture. So an azeotropic mixture is a constant boiling mixture. What that means, its composition is not going to change. Remember, each time you boil it, the composition is supposed to change. However, for an azeotropic mixture, once you get to that point, its composition is not going to change. All right. So when it says explain clearly the result, you will let them know that because it's an azeotrope, once you get to M, it behaves as a constant boiling mixture, and you cannot get a richer. All right, so you're going across, you cannot get more than, let's say, 50% A. All right, that is what it means. Okay, so once you see the 2 points meet, it's an azeotropic mixture, and you're not going to get 100%. All right,
Sir, when you're
apart
done this,
from that, sorry, please repeat.
when you finish this, I want to ask a question on mass spec. Just one simple something.
All right, right. So the next thing now, when you see all right, I'm just going to point it out on the next page. Those graph, right? When you see it curves, if it curves upwards, just know it is positive deviation. All right, that's all I can tell you for now. So if it curves upwards, it's positive. sorry, hold on. This is boiling point. Sorry. So for boiling point, when it's upwards, it is negative. All right, negative deviation. You see, if it curves downwards, it is positive deviation. All right, from Rhodes law. Talking about deviation, I'm talking about deviation from Rhodes law. All you need to know, if you're asked to draw it, just draw a line coming downwards for positive deviation and upwards for negative deviation. So this
Wait,
graph
sir.
here, it is positive deviation. Hmm?
Go back, please.
This,
No, with the positive and negative on the screen, chassis.
right? This. So right, if they ask you to draw it, you would, yeah. So you would just have this. So this would be negative. Sorry, this would be positive deviation. All right. And this one would be negative deviation. All right. Now, for this on the y-axis, it must be boiling point. All right. So this is negative and positive deviation when we are using boiling point, the required pressure as well. All right. So when it comes to this topic, know how to draw a graph of positive deviation and negative deviation. But this is the one for boiling point. All right. Boiling point, it goes down. And for positive downwards, negative upwards. If they ask you for vapor pressure, all right, they can get vapor pressure and they can get boiling point. Is pressure, right? No. Are you hearing me? Because it looks like the internet is freezing again. Shaniqua? And if you yeah, hear me?
Yes, sir. They are freezer like
Right, that means say so make it a freeze. It's still a freeze? Are you hear me now? Yeah, hear me? Oh, they just like it a freeze
yes.
on. Alright. Where was I? Right. So let me tell you. So two important things, right? When it comes to this topic. This graph here, you should be able to draw it right and explain the principle. You just pick anywhere on the x-axis, right? And you just draw a line across, come down, and you draw one next one across, come down. All right? Until you reach the end. All you need to tell them to get some marks is that from the graph, you can see that each time you boil the mixture, you are getting a vapor that is richer, in this case in A, right? So you would label it. So each time you are boiling the mixture and condensing it and re-boiling it, you keep getting a mixture that is richer in A until you eventually get 100% A. Then now they can ask you to identify, so they can show you some diagrams and ask you if it's like positive deviation or negative deviation. If they ask you to draw it, you just do this, right? With the, as I have it here. So you just draw the two axes. If they say show positive deviation for boiling point, right, you do this. Now, if they tell you to do it for vapor pressure, you are going to do the opposite. This would be for vapor pressure, and this would, right, so these two, hold on, give me a second. Right, so for vapor pressure, right, this would be negative deviation. So it's negative when it's higher than expected. So the reason why it's curved like this, it is higher than expected. So this is, so for vapor pressure, this is negative deviation. All right. And the next one for vapor pressure again, this one now would be positive deviation. Hold on. Let me just move this, move this, move this. All right. So it is positive deviation. So it's two graphs and they are opposite. So notice when it's for, when it curves down, right? In one instance it's positive, in the next, hold on. It's supposed to be the opposite. Oh, sorry. Hold on. When vapor pressure is higher than expected, am I mixing up something? Give me a second. So when you have a higher vapor pressure than expected, that's a good thing. Sorry. So it should be positive, right? Oh, yes. I am right. As I said, it's supposed to be the opposite, right? So when the vapor pressure is higher than expected, that is positive deviation. But when the boiling point is higher than expected, that is negative deviation. So when the vapor pressure now is lower than expected, that is negative deviation. All right. And when the, right, so for vapor pressure, when it is lower than expected, it is negative. All right. So that is why when you look at this, right, it's boiling point, and it's, if it was a boiling point for a particular compound, right, once it slopes downwards for boiling point, it is lower than expected, so it would be a positive deviation. All right. So final thing with Rhodes law, right? You should get a straight line. Let me use a different thing. You should get a straight line. Good. So let us say this is boiling point. All right. When it is lower than expected, so the red line is what is expected. So when it curves downwards, it is lower than expected. So this is positive deviation. All right. And if it is above the line now, that is negative deviation. All right. Yeah. So that is where the positive and the negative is coming from. The straight line is what is expected. So the straight line is for an ideal mixture. All right. So an ideal mixture, it obeys Rolle's law. And the non-ideal mixture now, with those are the ones that deviate from Rolle's law. All right. Yeah. So this one here and this one here, those are non-ideal mixtures. The one that gives you the straight line would be the ideal mixture. So when we talk about deviation from Rhodes law, those are non-ideal mixtures. So again, for boiling point, if it curves downwards, it's positive, upward it is negative. If they put vapor pressure on the on the y-axis instead. So if it's a vapor pressure curve, downwards is negative and upwards is positive. So you can clearly see that when vapor pressure is low, boiling point is going to be high. All right. So when vapor pressure is low, boiling point is high. When vapor pressure is high, boiling point is low. As I was saying, I have a recording for this. It's not made public, but the exam is tomorrow. So I'm going to make it public if you want to look at the recording on this topic. All right. Yeah. So just remember this, how to interpret this versus this. Once the two lines meet, it's an azeotropic mixture. Let me just look for a blank page. That is why you cannot get 100% ethanol. Should I draw this? All right, let us do this quick and end it. It says draw a fully labeled boiling point composition curve for a mixture of ethanol and cyclohexane, which forms an azeotrope. So once you see azeotrope, you know the two lines must meet. All right, so forming an azeotrope at a boiling point of 64.8 degrees Celsius and a mole fraction of 0.430. All right, so let me just quickly do this. Oh, no, sorry. So I would need this, right? So we're doing ethanol and cyclohexane, right? The boiling points of ethanol and cyclohexane are 78 and 81. So let us say, all right, let me put ethanol over here. Ethanol is over here and cyclohexane is over here. All right, hold on. Sorry, let me, I just want to move this. All right. So cyclohexane is on this side. All right, so if ethanol is over here, right? Notice, just for explanation purposes, right? On this graph, it is in percentage, right? Sometimes it is in mole fraction. So for mole fraction, if cyclohexane is out here, you are going to have 1 mole of cyclohexane, all right? And 0 mole of ethanol. And out here, you would have 1 mole of
It don't matter
ethanol.
where you put the ethanol and
Right,
the
so,
cyclohexane.
no.
Okay.
Right, so this would be 0. Hold on. So 1 ethanol, right? And 0 cyclohexane. And out here, it would be 1 cyclohexane and 0 ethanol. Hold on. And 0 ethanol. All right. So remember this vertical line, it would represent pure cyclohexane. All right. And this vertical line is pure ethanol. So it's like saying 100%. Now the boiling point says what? 81 is for cyclohexane. So if I'm going to put 81 here, so that means I'm starting here. And 78 is for ethanol. So let us say here is 78 degrees Celsius. So my curve should start at 78. Sorry, should start at 81 because over here is pure cyclohexane. And on this side, it should be 78, which is pure ethanol. So I would draw a curve from here. All right, let me make it a little higher so I can get the curve. And so let me let me put the 81 up here. All right, hold on. All right, so I'm going to draw a curve now. Come down here. All right, and that is my liquid composition. And you're going to put one above it now, which is it's, hear me? I think it's freezing. Shaniko, are you hearing me? Because I think it's freezing.
They are freeze a little.
Yeah, hear me better now?
Yeah.
All right. Let me go, let me go back to the diagram. All right. Let me undo this. Right. So you draw a line connecting the two boiling points. That is the liquid. That is the line for the liquid. And then you put one above it for the vapor thing, or a non-azeotropic mixture. So if you were doing a non-azeo, I think I'm freezing up. It would be a non-azeotropic mixture. All right. So if you were doing a non-azeotropic mixture, this is how it would look. Let me show you what you do now since it's an azeotrope. It says an azeotrope, which forms an azeotrope at a boiling point of 64.8. So this is going to be adjusted. So the lowest for ethanol is 78, but the azeotrope, it occurs at 64.8, right? Next, it says at a mole fraction of 0.43 ethanol, so and a mole fraction of ethanol of 0.43. So looking at this, right, if this is one ethanol, in the middle of it would be zero point 0.5. So zero point 0.4 would be about here. So this would be 0.430. So we're going in this direction, all right? This direction. So what is going to happen? The liquid line, all right? Let me come back here. So on this, right, where you see the two lines meet, it would be like right here, right? So this would be the 64 and this would be the 0.43. So I am going to make the two lines touch at a temperature of 64. All right. So I'm going to make the two lines touch at this point. So if you are doing an azeotrope, you are going to make the liquid line and the vapor line touch at a temperature of 64.8 and a mole fraction of 0.43. So it's like they're going to intersect at this point. So let me just adjust it now. So so you're going to draw your liquid line down to this point. All right. So remember, this point, it is in line with the temperature of 64.8 and the mole fraction of 0.43. I'm just going to move up this 78 a little bit. All right. So I'm going to put 78 there. All right. So, right. And then now you are going to draw it going up. So it comes down, right? And then you draw it go up. And then the liquid line now, I mean the vapor line, you draw it come down, make it touch, and then goes up. All right. So let me read the question again and just take you through it. So it says, draw a fully labeled boiling point composition curve for a mixture of ethanol and cyclohexane, which forms an azeotrope. So once you see the word azeotrope, it means that the two lines must touch each other, but they're going to touch at a specific temperature and a specific mole fraction. So it says, so you're going to read it like this. So when it says forms an azeotropic mixture at boiling point, so basically you're going to make the two lines touch at a temperature of 64.8 and a mole fraction of 0.43. So when you hear that, right, you put the temperatures. So, and they show the temperatures for what? Ethanol and cyclohexane. So, you, if you put cyclohexane out here, right, so you ensure that the 81 is literally higher than the 78. So the higher boiling point is here and the lower one is here. Now the 64.8, that must be on your graph. So you have to put the 81, the 64.8 and the 78. Alright, put everything on the graph. So you also know on the x-axis, you're going to put the 0.43. Now remember, based on the labeling, right, this axis here is 0% ethanol, and this one is, sorry, 0 moles of ethanol, and this line is 1 mole of ethanol. So the 0.43, it will be close to the middle. Once you do that, right, all you need to do, draw the line come down to, so put the point that intersects with the this temperature, right, and this mole fraction. And all you need to do now is draw the liquid line to the point and then draw it again to the boiling point of ethanol. So you start out at the higher boiling point down to where you have the azeotrope at 64.8, and then you draw it up back now to the boiling point of ethanol. And then you just do the same now for the vapor composition. All right. So what I was saying, right? You see this now, you could not get 100% ethanol because you see when you start out here, sorry, when you start, if you start with this mixture, right? You draw it here, you come here, you come down, right? You do this, and then you do that. Once you get to this point, you are not going anywhere else. All right. Once you get to this point, that is it. You cannot separate the mixture anymore. So fractional distillation, if you have an azeotropic mixture, you cannot use fractional distillation to get 100% of it. If you want 100% of it using fractional distillation, don't start don't start with a mixture less than 0.43. You would have to start with more than it and then go across. All right? Yeah. So that is basically it. So for this, just know how to draw the graph, all right? And remember the deviations, all right? Yeah. So that's it. All right, 3 minutes, and then we end. I'm going to show you IR just to interpret the graph, and then we end there. All right, all I'm going to, how do I do this quickly? All right, give me a second. Because it's now 11 o'clock. All right, let me just, where did I put the pen? Give me a second. It's now 11. All right. All right, when you look at this for IR, you're going to, all right, so OH, you're going to have your data booklet with the wave numbers, all right? You're going to be looking for functional groups. So you can look for OH, you can look for the carboxylic acid functional group, You can look for a ketone, right? Or you can look for an ester, all right? The OH, it's at about 3,400, all right? When you're looking for a C double bond O, it will be between, it's about say 1600 to 1800. If you're looking for a C single bond O, it's at about, it's close to a thousand. So let's just say 1,000 to 1,200. But it will be on the data booklet, right? So, and this here, don't pay anything. This peak, it's a CH peak. It's not important. So CH is at three, close to 3,000. All right, so I'm just going to put 3,000. All right, when I look at this, right, I see a band coming. So you only look at the peaks that are almost touching this line, so very close. So this, and this as well. All right, but this is a CH peak, so it's not important. This one now at 3,400. Once you see it at 3,400, it's alcohol. All right. So we see an OH band coming down. So justification. So this compound, it would be an alcohol. Justification. I see a band at it's about 3,400. So band at 3,400, which is equal to the OH group in alcohol. All right. But Vidan, this is also on the channel. When I look at this one now, right? This would be, all right, so this is my CH. It can't help me. There are no OH bonds here. So if you look at this is an OH bond above the 3,000 number, right? When I look at this, there is nothing above the 3,000. So it couldn't be an alcohol. The CH, every compound has CH, so that can't help. The next thing I see here is a bond at about 1,700. So that is C double bond O, right? And then this one at about 1,200, which is C single bond O, right? At about 1,200. Let me see if I had put the question in it. No, I just have the charts. All right. Oh, here it is. So we are trying to identify an ester, a ketone, an ester, a ketone, and an alcohol. All right. So I already identified that this would have been the alcohol. So the OH group in alcohol. The next one now, I see C double bond O and C single bond O, right? Which means that it would be an ester because ester has C double bond O, C single bond O. So all we're doing with these charts is identifying the functional groups. All right. So there's no OH because there's nothing at above the 3,000 mark. What I see is a line at the about 1,700, a band. All right. So a band at 1,700, which is C, which is equal to C double band O. And I see a band at approximately 1,200, which is 1,200. So that is C single band O. That is why it is an ester. Double band O, single band O. All right. With the alcohol, you have OH, and you could also have the C single band O. This one is not important for alcohol though. All right. So alcohol is C, O, and H. All right. The next one now. This is CH, not important. This would be the ketone. because I see the next line again, it's at about 1700. So bond at 1700, which is the C double bond O, and you don't see anything else other than the CH bond. Bond at that's 2950, right, which is the CH. That is how I know it's a ketone. So remember, the ketone functional group is C double bond O. All right. So that is how you interpret the charts. If you only see the C double bond O, then it's a ketone. In terms of carboxylic acid, the OH, it will have peak. All right. So when you see a broad peak, it is still OH, but OH in carboxylic acid. So remember, you can have OH in carboxylic acid, and you can have OH in a regular alcohol. So both of the just know that if you see a much broader peak at around the 3000 mark, so starting like from here to here, that would be the OH in carboxylic acid. So this would have been a carboxylic acid. But when it's much more slimmer, right, like there, that's the OH non-alcohol. All right, and that is where I'm going to wrap it for tonight. All right, yeah. So remember, it will be on the channel as I end it. Just click on the live tab. If you want the booklet with the answers, just send me an email, or if you have my number already, WhatsApp me. All right. Remember, for module 3, try to just study some key information. Whichever process you're studying, it will have an impact on the environment. It will also have uses. So just study at least 3 uses, 3 impact on the environment. They are going to have equations. So like for the Haber process with the chlorine, the reaction at the anode and the cathode. Let me just explain one thing with, should I? Yeah, let me just explain it. Let Chatelier's principle, right? Module 3. Mm, SO, what is it again? SO2 plus O2 to give 2SO3, right? Negative something. Let's say 108, right? If you want to maximize the amount of SO3 you get, you are going to decrease the temperature, all right? So just remember now, if you want to maximize the yield, all right, if you want maximum yield of SO3, you are going to decrease decrease the decrease the temperature and increase the pressure. Well, all right, decrease the temperature and increase the pressure. That when you do that, the system will shift the equilibrium to the right hand side, and so it will produce more SO3, and it is the same for ammonia. So just remember, decrease the temperature and increase the pressure. Both of them will cause the equilibrium to shift to the right hand side. All right, yeah. So the right hand side has fewer moles. So when you increase the pressure, it will shift to the side with fewer moles. All right. Yeah. All right. I think I'm going to end it there. So all the best. All right. Yeah.
What about temperature, Professor?
All right. So for temperature, when you increase, well, did I say increase? No, decrease. Right. So when you decrease the temperature, right, the forward reaction it is exothermic. All right. So because the forward reaction is exothermic, if we decrease the temperature, the system is going to increase it by shifting it to the right hand side. So over this, when I say shift it to the right hand side, this side will cause the temperature to increase because it is exothermic. How you know? The negative sign on delta H. All right, so at the end of the equation, you will have a value for delta H. So because it's negative, it is exothermic. So the forward reaction is exothermic. That is why we decrease the temperature so that the system will shift the equilibrium to the right hand side. All right, as that will cause the temperature to increase. All right, so just to repeat, you're going to increase pressure so it shifts to the side with fewer moles, which is this side. 3 mole is over here, 2 mole is over here. So when you increase pressure, the equilibrium shift to the side with fewer moles, which is the right hand side. And so you are going to get more SO3. When you decrease the temperature, the equilibrium is going to shift to the exothermic side, which is the all right. So to increase the temperature, the system has to shift to the right hand side. And wherever it shifts to, the amount of substance will increase. So that is why for the Haber process, for the contact process, high temperature, sorry, low temperature and high pressure is used. However, they can ask you like a compromise is made, right? And the reason why two things in terms of temperature, you can't use a low temperature because the catalyst V2O5 vanadium or pentoxide, it works best at, I think you can check back in this study guide, but I think it's about 340 to about 450 or 400. I think it's 400, but you can check back, right? So the catalyst works at 340 to 400. So even though decreasing the temperature will increase the yield, you cannot decrease it too much because the catalyst works at a high temperature. So they have to make a compromise. All right. So if they ask you what compromise is made in terms of temperature and pressure, for temperature, because the catalyst works at 300 to 400 to 450, right? So somebody said 450, right? So 450. So the reaction is carried out at a high temperature. So not because, so ideally, so the optimal or the ideal condition is high temperature, sorry, is low temperature and high pressure. But they have to make a compromise because the catalyst works at a relatively high temperature. So they can't drop the temperature to like 50 or 100 or even 200. All right? Because this is where the catalyst is working best. In terms of pressure now, all right, they get a good yield at 1 atmosphere. So the amount of yield that they're getting for sulfur trioxide at 1 atmosphere, it is high. Now, if they wanted to increase it more, right, it would cost them in terms of energy. So they just settle. All right. So they would have to spend a lot more in terms of for energy expenditure to increase the pressure. So they just settle at 1 atmosphere. All right. So the reason why they don't increase the pressure further is because of energy cost. All right. And the reason why they don't decrease the temperature further is because of the catalyst. So the catalyst hinders the temperature, and energy cost hinders them from increasing the pressure. All right, yeah. So the ideal condition, so you have ideal, and then you have to accept reality. So ideally, it is low temperature and high pressure, and you tell them why in Le Chatelier's principle, and look for a definition for Le Chatelier's principle. So whenever you apply a stress to a system at equilibrium, the equilibrium shifts in a direction to counteract the stress. All right, so ensure you know Le Chatelier's principle. All right, so in terms of this, you know your raw material and the equation. So this equation, the formation of oleum. So know your raw materials, know the equation. If you get that, if there's a diagram, know how to label it. So specific information, raw material, any equation, know how to label a diagram, know at least three uses and three impacts on the environment. All right? Yeah. Because they're not going to accept all of this, but it can come from any of those areas. Equation, use, impact on environment, raw material. It doesn't matter if it's chlorine, Haber process, contact process. All right. I have a video on atmosphere and the channel and a little revision. All right. So you can look at it. All right. Yes. So I'm going to end it here. It's late. All right. So again, all the best tomorrow. All right. Yeah.
Okay, sir. Thank you.
Yeah.
Thank you, sir.
For me, if you probably you can probably, well, for me, but you can try the topics you prefer, but I will go with atmosphere chlorine, Haber process, contact process. All right, yeah. Atmosphere chlorine. The thing, pollutants, yeah, you can look back on pollution. All right, yeah. But those are the ones I would go with: chlorine, Haber process, contact process, atmosphere. Yeah. All right, have a good night. Let me end this now. Yeah. You're welcome.